So we have Kaiqing Zhang, an assistant professor at the Department for ECE and the Institute for Systems Research at the University of Maryland, College Park. He is also a member of the Maryland Robotics Center, UMIACS, and Center for Machine Learning. During the deferral time before joining Maryland, he was a postdoc affiliated with LIDS and CSAIL at MIT, and a research fellow at Simons Institute for the Theory of Computing at Berkeley. He finished his PhD from the Department of ECE and CSL at the University of Illinois Urbana-Champaign. He also received a master's degree in both ECE and applied math from UIUC and BE from Tsinghua University. His research interests lie broadly in control and decision theory, game theory, robotics, reinforcement and machine learning, computation, and their intersections. He serves as an area chair for ICML NeurIPS iClear UAI and is the recipient of several awards and fellowships, including Hong McCullough and Ellen Fellowship, Simons Berkeley Research Fellowship, CSL Thesis Award, IEEE Robotics and Automation Society Best Paper Award, and ICML Outstanding Paper Award. Kaiqing, take it away.
All right, thank you very much. Thank you very much for the kind invitation, and it's really my honor to be here. And also, thank you very much for the kind introduction. It's funny because there's a fun story. I sent the title and abstract a few weeks ago, and then I got to know yesterday that actually Asu literally gave a talk here at BU, covered our work, part of it, I would say, a few weeks ago. So I made some last-minute change yesterday. So I'll make sure, if no matter who if you have attended, if you haven't attended the talk, that's great. If you haven't attended the talk, so I'm sure it will still be very different. So I will put more like my personal take on this long work, and also I'm sure you'll see something different. Today I'm going to talk about independent learning stochastic games, where strategic decision making meets reinforcement learning. So before I forget, this is a joint work with a group of fantastic collaborators, Mohammed and Noah, which are like my close collaborators during my postdoc, and Xiangyu is my PhD student at Maryland, and my PhD and postdoc advisors. So we know that, I mean, I guess for this audience, I don't have to say more about the recent successes of reinforcement learning. It has achieved, especially the reinforcement learning theory has attracted increasing attention lately. And I'm using this figure to show, I guess, a very simple introduction of reinforcement learning. The goal here is try to make sure the autonomous agent can make sequential decision making in unknown and dynamic environments. So if you look at the self-driving car example, you view this car as an agent, then they're the state, which is here you can view the state as the position of the vehicle, the speed, acceleration of the vehicle, and the surrounding environment. And the car will take some action, it will either turn left or right, make some maneuvers, and there are also some definition of reward here. So it's like a very typical feedback loop for decision making and for control. But in practice, this is what's really going on. In practice, there are a lot of cars on the road, and they are interaction with each other. So how should we address this problem? And in fact, many more AI systems now involve multi-agent dynamics or multi-agent interactions. So that even one of the most famous successful stories of reinforcement learning was AlphaGo. So the Go games, if you will, the formulation there is a two-player, zero-sum, turn-based stochastic game. There are also some other examples like control of a group or a team of unmanned vehicles, or the fleet of robots in warehouses, or another very high-profile example was done by OpenAI, which was playing video games, Dota. They they trained the PPO or reinforcement learning agent to do this team versus team strategic games. Therefore, further advances critically depends on analyzing multi-agent interactions, decisions, and learning in dynamic environments. So that brings us to the world of multi-agent reinforcement learning. I personally have worked on it during my PhD on several different aspects of that. And some of the speakers and the audience here are also expert in this domain. Therefore, there has been a great lot of recent advances in this area, and there are many very interesting workshops or programs in the areas of controls, computer science, economics. It's a very interesting interaction of several important domains. Like there are several workshops new workshops in Simon's Institute, NeurIPS, Aclear, and CDC over the past several years. This area has grown a lot. So a very quick introduction from my personal take on this is so we can view the setting of multi-agent RL most people are studying as some block on the top right corner. If you view it like a single agent, if you want to solve a single agent decision-making problem in a static environment where there is no state transition, you can solve it using the tools we are familiar with in optimization. And what about RL? So reinforcement learning or solving an MDP corresponding to the right bottom corner, which is the case where if you have a single agent decision maker, but there is a Markov state transition there. Of course, that's also a stochastic optimal control problem we are solving in controls literature. On the other axis, if you have static problem, but you want to solve or you want to model the strategic decision making or strategic interactions of multiple decision makers, that correspond to the formulation of a static game. Or one well-known example is this normal form game or matrix game example. But what's really stochastic game? Stochastic game is a problem where you both have this multi-agent strategic decision-making process as well as the evolution of a state that's usually modeled as a Markovian state. It started with the model developed by Shapley back in the 50s, and then it was used generally in this multi-agent reinforcement learning world. So I worked on that, but there are something I've been thinking about always. The problem is why do we study this problem? Or why study multi-agent reinforcement learning? Or in general, I found it very intriguing to see this question while I was doing some literature review back and from this critical overview paper by Yoav Shoham from 2005. He was asking a general question, not only for multi-agent reinforcement learning, but multi-agent learning in general, which is, if multi-agent learning is the answer, what is really the question? So that kind of troubled me for a while. Is it really the polynomial sample and space complexity, or the sublinear regret, especially in the online exploration setting? Or it is more about faster equilibrium computation and its computation complexity? They are all could be possible questions. Or a more, I would say, fundamental or intriguing question is, does this multi-agent setting really provides new and unique perspectives for sequential decision making? So that's something I was very interested in. I was trying to or attempted to address. Hopefully, I can provide part of the answers in this talk. In other words, is finding equilibrium all we need? Okay, that seems to be the goal in many of the multi-agent reinforcement learning work. In fact, one traditional explanation of equilibrium, or in particular Nash equilibrium, is that it is a result from analysis and introspection by the players who knows the model, who knows the rules of the game, the rationality of the players, and the payoff functions. Think about the case where, the textbook examples of Prison's dilemma, how do you reason this is an equilibrium? That's a very traditional definition of equilibrium. But there's also an alternative definition from the learning in games literature. Okay? Learning here means slightly different things, as I will allude to in a minute. In this line of literature, people argue that equilibrium or specific Nash equilibrium is a good solution concept because it arises as a long-run outcome of a process in which less than fully rational players grope for optimality over time. In fact, equilibrium is not the target. Instead, it can be viewed as a natural outcome of some myopic and non-equilibrium learning dynamics. And by learning here in this literature, usually they are not talking about the learning we are usually talking about in reinforcement learning, which is mostly related to the fact that you don't know the model exactly. Learning here usually means you are learning from each other. Okay? And the equilibrium will emerge eventually if you do some very natural and simple dynamics during the learning process. So let me give you a very simple, quick example, which is fictitious play. So this perspective, the perspective I just mentioned in the previous slides, has been well established in this normal form matrix game example. So there is a book on learning games by Fudenberg and Levin. That's a very fundamental and comprehensive study. So fictitious play was first developed by Brown back in the 50s. It's probably arguably the earliest learning dynamics in this learning games literature. What it does is super simple and intuitive, which is from agent I, each agent's perspective, because I don't know what's the situation of other agents. I also don't know what's the situation of this game. What I would do is that I would maintain a belief. Okay, pi minus k minus I here means the other agents at iteration k, at time k. What I will do is that I will take a temporal average of the play here corresponds to the action in our RL language, of the opponent. Here is a setting where you assume you can observe the action taken by other agent. I will take a sample average. I will use that as a belief as if the agent or the opponent is trying to use a stationary policy according to this. Then what I will do is that I will select my action as a very simple best response against that belief I have. Okay? In this setting, as I said, there's no learning yet in the sense that, in the RL sense, in the sense that usually people need to assume you know this matrix QI. And then what I can observe is just the play of the other players. And then I will do a very kind of myopic and greedy action at iteration k. And what people can show, or what do we know about this dynamics? You can show that Nash equilibrium will emerge in the long run. And also it will emerge for several classes of matrix games, like I mentioned, including two-player zero-sum games, identical interest, meaning the reward is the same for all the players. It is usually used to model a cooperative decision-making setting. And also some 2x2 non-zero-sum matrix games. These are like very classical results. It's claimed to be natural, it's symmetric, also it's implemented symmetrically between the agents, and independent in the sense that each agent just runs this dynamics individually. You don't need to coordinate with other agents in this kind of implementation. That's why we want to take this learning in games perspective into this multi-agent RL world. So is this also true in stochastic games when we have state dynamics, okay, like we did in RL setting? Or if not, in general, of course, even in the static game setting, it's not generally true. If it's not in general, maybe it's fine to just embrace it in the sense that we can probably view this dynamics itself as some solution concept instead of finding or computing equilibrium. And this is something also inspired me when I was at Simons. Like Christos gave a talk, he said, you may want to be like impressed of the game dynamics, or you just let agents run the the natural dynamics, and you let the dynamics show you the way. Okay, there are some. We also got some inspirations from this kind of perspectives. On the other hand, those are more like the things from the learning games literature. But on the other hand, in really like multi-agent RL world, independent learning, which is usually defined as following: each agent runs some variants of single-agent reinforcement algorithm, say Q-learning or PPO, to myopically improve her policies, and sometimes even obvious to other agents or the type of the game. And technically, independent learning is known to suffer from some convergence issues. There are some old papers that give examples showing that, let's say in two-pair zero-sum case, if you independently run like value iteration, it wouldn't converge. Okay? And the key issue here is because in the multi-agent setting, there's the issue of non-stationarity, because other agents are also adapting their policy. Therefore, many of the assumptions we had in analyzing single-agent reinforcement learning algorithms do not hold anymore. So, but practically, independent learning seems to perform pretty well, at least much better than I expected before. We have seen like papers, especially empirical multi-agent RL papers with a title like, is independent learning all you need in playing StarCraft multi-agent challenge? Or like the surprising effectiveness of PPO in cooperative multi-agent games? Or independent algorithm can perform on par with multi-agent ones in cooperative and competitive settings. This brings us to raise the following question of interest, which is, can equilibrium be realized by natural and independent learning dynamics in stochastic games? If so, in some cases, then it might in turn justify the success of independent learning in multi-agent RL literature in these certain cases. But if it's not, in general, is there any possible fundamental reason for that? So this is a very quick introduction of the setting we study. Okay, you can view it as a generalization of Markov decision process in the multi-agent setting, what we call stochastic games. Here we focus on the infinite horizon discounted setting. It can be characterized by the following tuple. S here is the set of the states. AI corresponds to the set of actions of player I, and Ri denotes the reward function of player I, and it is affected by the state, S, and the joint action, or action profile we call it, which corresponds to the action of all the agents. There are several very structured settings here. For example, in two-player zero-sum games, you have the case where n equal to 2, and the summation of the reward function for any state joint action pair is equal to 0. And each player I will take action AI, and then the state transition to another state according to this transition kernel, which is also, again, affected by the joint action of all the players. If there is only one player, it reduces to the Markov decision process model we had in reinforcement learning. And the gamma here is some number lies in 0 and 1, which is a discount factor. Okay. So the solution we care about is, for short, we call it Nash equilibrium, but in fact, in general, you should call it more rigorously. It's a Markov stationary Nash equilibrium. We are looking for exactly the same type of policy you had in infinite horizon discounted single agent RL, where you are looking for a policy pi I for each agent I that maps from the state S to a distribution over actions AI. And then you can similarly define the expected value function of player I as Vi pi, but note that the pi here is a joint policy that depends on all the agents' policies, okay? Because of the coupling in the transition dynamics as well in the reward function. And then it's, the value function is nothing but the accumulated discounted reward, expected reward, starting from a specific state. And then the definition of Nash equilibrium in this case, or Markov perfect stationary Nash equilibrium in this case, is a pair of strategy pi star, or the tuple of strategy pi star, such that the following inequality holds in the sense that if you fix others' strategy or policy as pi star minus I, there is no incentive for me to deviate from that. Okay? And also, it's a perfect equilibrium in the sense that we need that to hold for all the states, like we required in the solution we had in single agent RL. They're all corresponding to each other. Our results in one sentence is that independent learning made simple in the sense that we identify simple independent learning dynamics with convergence guarantees to the Nash equilibrium in certain stochastic games. And the learning dynamics require no explicit coordination among agents, is symmetric and arguably natural. And also, each agent is unaware of the type of the game. For example, whether the game is zero-sum or identical interest or not. And sometimes even unaware of the existence of other agents. More specifically, we give a name to this dynamics. We call it decentralized Q-learning. So we consider a best response type of learning dynamics where the action or even the action set of the opponent cannot be observed. So before introducing the learning dynamics of the algorithm, let me first introduce intermediate notation here. We call it local Q function to better understand the idea in our learning dynamics. So local Q function of player I is defined as a Q value function, marginalized with respect to the opponent's strategy pi minus I. Later you will see that it will be estimated or updated at each iteration. By doing that, we say local means that because of that, the Qi, small Qi right now, is only a function of the state and the action of your player I yourself. Okay? There are two main steps in this learning dynamics. So first step is that the player I will try to infer the opponent's strategy by estimating the local Q function, because from the definition, you'll know that you have to know the opponent's strategy, pi minus I, to really compute this Qi, small Qi. But in fact, you can do it implicitly by doing the following update rule, which is kind of similar to the Q-learning dynamics we have seen in single-agent RL, but we made a small trick to make it work. So trick here is that it's kind of related to the target network idea in deep Q-learning, where you are doing the following update. You maintain an estimate Q hat of this Q hat I as this estimate of this Qi. This is kind of like a temporal difference type of update, but instead of taking the argmax of this Qi at iteration k, you replace it by another variable v hat I. Here, the AKI is drawn from a softmax or like smooth spatial response distribution against my current estimate of Qi. Okay, the tau here is some temperature parameter, and nu I here correspond to some perturbation function. And there's a name in the learning games literature which they call smooth spatial response. But also you will know that if you choose this nu I to be entropy function, this argmax will give you a closed form solution, which is argmax. You take that action as player I, which is AKI. And then in the second step, the player I will estimate the value function v hat I in the following update. I will use my smooth spatial response times the local Qi estimate and move toward that direction. So all the quantities we are updating here are maintained locally without coordination or explicit communication, and they are symmetric among the agents. And in fact, this was very different from many existing provable multi-agent RLs. I have to be careful here at that time because the area is growing very fastly. There are several more recent results that can also do things like that. So this is a summary of our learning dynamics. One key feature of this learning dynamics is that it's 2-time scale. In the sense that if you notice in these two update rules, we use different step sizes, alpha and beta. It's 2-time scale in the sense that as the time goes to infinity, the ratio between the beta and alpha is going to 0, in the sense that the beta is relatively small as time goes by, which means that the first step is updated much faster than the second step. Therefore, you can view it as a case that in the first update rule, the V is relatively stationary. So we created some stationary environment to solve this problem in the first line. So as if you can show that actually by doing that, it is as if solving an auxiliary normal form game with the following payoff matrix. Okay? As if you fix this V hat I in the limit. By doing that, you are solving for the equilibrium of this matrix game, and then you plug into the outer loop or like the slower timescale update rule that will give you the update rule as a stochastic approximation of the minimax value iteration algorithm to solve, let's say, 2-player zero-sum stochastic games. That was exactly the game proposed by Shapley's original paper to solve this 2-player stochastic game. And that's actually the key to the convergence proof, is to create this 2-time scale separation and create a relatively stationary environment for the agent. And also another feature of this dynamics is that this time scale separation may also find some evidence, or actually we got some inspirations from the evolutionary game theory and behavior economics literature, where they did some experiments showing that players' choices are usually more dynamic than their preferences. For example, you have a preference of the restaurant nearby, and every day you have to make a choice. But your preference of which restaurant is better may change over time, but usually it may change slowly, or relatively slower than how you make the decisions. In that sense, you can view the payoff estimate, the V hat, as a preference, and every time you are using that as if it's relatively stationary to make your instantaneous best response decisions. Last one I want to mention here is that this dynamics is oblivious to the presence of the opponent. There's a name in this learning games literature to call this type of dynamics. They call it radically uncoupled dynamics. What we first show here is that in the 2-player zero-sum, very basic case, 2-player zero-sum stochastic games, okay, if you set, the key here is to make sure the step sizes satisfy this 2-time scale separation. And also you have to decrease your temperature parameter appropriately. then you can show that this v hat I will converge to the Nash equilibrium value of this two-player zero-sum game almost surely. And also, if you use the step size to average the policy you have been using during the learning process, it will converge to the Nash equilibrium strategy almost surely. Also, because the dynamics is best response type and also is symmetric, there's also a corollary from this result, showing that this learning dynamics is not only convergent, which is a very important property you need for learning dynamics, but also rational, which was something defined by Bollinger and Veloso in the literature, showing that an ideal multi-agent learning algorithm should be rational in the sense that if the opponent is using stationary policy, you should be able to naturally convert to the best response to that. In the sense that if the opponent is a weaker opponent, you should be able to exploit this fact, exploit this weaker opponent. It's called rational in their paper. Because of that, it will easier for you to justify that the agent will follow this dynamics in the first place. You can show that this learning dynamics is also rational in this sense. It converts to the best response to this agent, to the opponent. So how far can we go with such learning dynamics? Okay, we showed the convergence in two-player zero-sum cases. What's next? In fact, I want to mention that, something I want to talk about now is that one desired property of this independent learning, why do we care about that, is that it is game type agnostic, as I mentioned several times. Recall this fictitious play dynamics. So you first have a belief update by just observing the plays or the actions, histories of the opponent. And then I'll take a simple best response. The same update rule from each agent's perspective, from local perspective, it's the same update rule, but they converge in a class of algorithms, games. Therefore, in the literature, people call this if a game has this fictitious play property, if fictitious play converges in this to equilibrium in this type of games. It's not a universal result, but it will help us understand the interplay between this natural dynamics and certain games. Then my question, or our question at that time was that, what about stochastic games? Are this kind of fictitious play property kind of universal across stochastic games? The answer is yes, in some sense, in the sense that if you also use this 2-time scale step size separation as our decentralized Q learning, you first maintain a belief like we did in traditional fictitious play, and then you update your Q value function in a slower time scale. So Q here will literally give you the payoff matrix for that auxiliary game I just mentioned more explicitly. And then you update that as if you are using that as solving a matrix game, where the action is taken from this best response against my belief of the opponent, as well as the payoff matrix. We can show that this very same fictitious play dynamics, or some smooth version of that, in the sense that if you're not taking best response, but like a soft max of that, it will converge to Nash equilibrium for zero-sum case, two-player zero-sum case, which is a strictly competitive setting, as well as n-player identical interest games, which is a cooperative setting, and multiplayer zero-sum games. That's a relatively new model we developed, which is kind of, you can view it as a mixed setting. It's not completely zero-sum, but it's like the agent has like network interactions with each other, and the reward sum up to 0. It's a very new model we developed for stochastic games. In other words, FPP is kind of universal in stochastic games for this class of games. That's so far what we can show. Another intriguing question is that those are the games with certain payoff structures, right? So what about general sum cases? Okay, what's the limit there? How far can we push? In fact, there is I would say, relatively underestimated paper by Zinkovich, Greenwald, and Littman back in 2005. It's a very interesting result. They show that value iteration or value-based methods cannot find a stationary equilibrium in general for general sum stochastic games. So what they did is that they construct some counterexample. It's a term-based general sum stochastic game. They show that there exist two models. They have different equilibrium policy, but they have the same value function. You cannot distinguish the equilibrium from either one of them by only looking at the value. They also give some other fix to this kind of counterexample. And our decentralized Q-learning cannot either, because as I mentioned, it converges rely on this gamma contracting property of min-max value iteration, which breaks easily in general sum case. What I mean is that if you do this value iteration at this round, if you solve a Nash equilibrium, and then you keep doing this iteration, we are not sure if this operator, value iteration operator, is contracting or not. Because of that, it's unclear how to construct a stationary equilibrium from non-stationary ones. Because in single-agent RL, as even the first speaker mentioned, the truncation is very important. If you have a long enough truncation with a discount factor, like the horizon has to scale with 1 over 1 minus gamma, you can truncate the learned policy and use your policy at time 1 and play it stationarily as a stationary solution. It could be a very good approximation of the problem. But the key there is because of this gamma contracting property. If you don't have that in this case, then is there a fundamental reason why infinite horizon, general sum, stochastic games are challenging, other than just these counterexamples? So there might be one, in the sense that we recently showed that finding Markov stationary equilibrium, no matter it's Nash or correlated or coarse correlated equilibrium, in general sum, even two-player, even a constant gamma equals to 1/2. Equal to 1/2 means that in expectation is just a two-stage game. Finding this equilibrium is PPAD hard. So PPAD denotes for polynomial parity argument on directed graphs. It was a class or problem that was believed to be intractable computationally. And there is a very interesting saying from this literature is that if your laptop cannot find the equilibrium, then how can the market or how can the human? But it's not contradicting with many of the results in the learning games literature, because usually there people care about asymptotic emergent behavior, which is also a very significant result. One thing I want to emphasize here is that this is in stark contrast to normal formal static games, because we know that in static normal form games, if you are looking for Nash equilibrium, for general sum, it's PPAD hard, it's intractable. But there's a fix to that, which is if you relax the equilibrium you are looking for example, you relax that to coarse correlated equilibrium, you can solve it using linear program. So it's a tractable notion. But here, what we show is that if you have this sequential decision-making setting, even finding CCE is hard. This kind of shows the unique challenge in this sequential strategic decision-making. That's not covered by either the single-agent MDP case or the multi-agent static case. However, if you relax this solution concept from the stationary one to non-stationary, where you are looking for a sequence of policies that depends on time, you can actually develop decentralized learning algorithm with polynomial sample complexity. And note that decentralized here will give us the result that it will even be polynomial in the number of agents. It will not grow exponentially in terms of number of agents. So I guess I'm running out of time. So the last question we are interested in is what about partial observable cases? That's the most question I got from after giving talks to people and talking with people, especially with engineering applications. In many of the learning dynamics you develop here, or the algorithm we develop here in the multi-agent RL world, we need to assume you have access to the state S. But it's usually not the case. Actually, it's rarely the case. Additionally, in the multi-agent setting, each agent may not have each other agent's observations. This is what we call asymmetric information structure. And also, that's also the case in decentralized decision-making in general. This is a very challenging setting. There are actually many known hardness, fundamental limit hardness results in the literature, starting from the results in decentralized stochastic control, as well as some complexity hardness result in decentralized decision-making in general. So can we better understand the provable efficiency of partial observable multi-agent RL? In fact, we can make some progress. We actually made some progress recently, showing that it's possible to achieve the quasi-polynomial sample and computation complexities when agents share a certain amount of information. And the interesting thing I want to mention here is that this is the idea we borrow from literally from decentralized stochastic controls literature. They call it common information-based approach. In there, actually, this approach can give you a very neat dynamic programming, but the computation complexity was not there, was not clear. We show that it's possible to achieve quasi-polynomial sample and computation complexities by sharing this information, which is a very natural idea, and it is usually the case in practice. So to conclude, so we started independent multi-agent learning in stochastic games, a very old model back in Shapley's work. Several takeaways here is that, so if multi-agent RL is the answer, so maybe justifying equilibrium as a natural emergent behavior of independent non-equilibrium adaptation dynamics might be one question, among many other significant ones like sample and computation complexity, online exploration, regret, and convergence speed. Despite the non-stationarity issue, decentralized Q-learning can converge to Nash equilibrium with a 2-time scale step size separation between the value function estimate and the strategy update. And fictitious split property are kind of universal, or this game agnostic convergence are kind of universal in stochastic games. And infinite horizon stochastic games could have sharp and fundamental differences from finite horizon games and infinite horizon MDPs. And lastly, the probability efficiency for partially observable multi-agent RL is largely open. We need more ideas from the literature to really tackle this challenging problem. And thank you very much.
Thank you so much for the incredible talk. Any questions for Kaiqing? Please answer. Please, we have some time for questions.
Thanks for the talk. So I see that in the decentralized Q-learning algorithm, you have an inner product between the action and the Q value, and so you want to select the best action. So in that case, is this algorithm only working on the tabular setting? Does it work on continuous control setting?
Yeah, good question. So this result is for a very basic, like tabular case. We had a follow-up paper to deal with a case with linear function approximation, but not for general like continuous space. We don't know actually. But for linear function approximation, like we did in the Q-learning with linear function approximation, you need to do your temporal difference update in a specific way. So you can handle that. But in this result, we can only do that for the tabular case. Yeah.
Could you go to the slide about the best response learning dynamics?
Okay.
Yeah, so when one agent, or maybe it's even somewhere else, but when one agent is like estimating the policy or like their Q function, the dependence on all other agents' actions, like how are they actually able to evaluate the expectation with respect to others' actions? They need to track an average action or something?
Exactly, that's exactly the point here is that the QI here, like in this line in definition, you need to do the expectation. But in fact, this is just a table you are maintaining, like you did in even single agent Q-learning, right? You use a table, and then you use a stochastic approximation algorithm to estimate this table. And then in the limit, because you are interacting with this agent, which is also very important, it's an online algorithm, you are able to recover an estimate of this expectation. So exactly the same as the things we have seen in stochastic approximation and Q-learning.
Okay, so now my question.
Yeah.
So what if agent I, J, K, et cetera, like all have different like policy representations that are like feeding into their action selection? Like say one of them is a risk-sensitive policy and one of them is a risk-seeking policy and so forth. Is just observing the sequence of actions enough to still estimate the same pies, even though they could be coming from statistically totally different underlying policy is?
Yeah, that's a very good question. So we don't know in the sense that in this case, or in many of the very basic results in learning and games, you are implementing this in a symmetric way. In the sense that if you are doing this, you are also assuming, or like in order to make sure the algorithm will work, the equilibrium will emerge, the agents are kind of homogeneous. They are following, both of them are following this dynamics. And also that's actually a good thing about this from this single agent perspective is that no matter what other people are doing, I'm just following this. And whether equilibrium will emerge or not, depending on this combined effect of that. But let's say if you change the setting to a more heterogeneous case, then I guess in general, even in the matrix game setting, we're unsure what will be the emergent behavior there. So that's a very interesting question to investigate, I believe.
Yeah, exactly, because like you could impose like bounded rationality and
exactly,
and then
exactly.
As soon as you don't assume that everyone has the same definition of rationality, then
you could have different emergent behavior, not necessarily the Nash equilibrium, but you could probably have something else.
Like quantal response equilibrium.
Yeah, it's possible.
So I guess there's different kind of philosophical perspectives you could take on this. One is that you're designing an algorithm for many agents.
Yeah.
But if you think of yourself as modeling the behavior of people or something, as is often done in this literature, I guess I'm wondering how you think about what is a natural strategy to really assume people are following. Like, should I imagine that people are this local and incremental in how they change their actions?
Right, that's a very good question. This is really the philosophical question that we're asking ourselves also. What's really a natural dynamics? So I guess from this literature, usually they tend to model it from a human behavior perspective. So let's say the smooth or like the fictitious play or smooth fictitious play. There are some literature showing that if you really do the experiments with human, they are kind of doing this kind of dynamics. But to us, it's kind of, because we want to show some more theory, it's kind of, we are moving towards the algorithm part. So in the paper, or even most of the talk, I would like to call it learning dynamics instead of call it algorithms. But I agree, it's not completely, so in my opinion, what's the most natural independent learning algorithm in this setting would be vanilla independent Q-learning. So I'm just a single agent, I don't care what's going on with the world, I'm just running my own version of Q-learning. But unfortunately, we are not able to show it converges. We are kind of using this more like change-out variable, like the 2-time scale separation, to make it kind of like a Q-learning, but slightly different. And also, we want to justify this 2-time scale separation from some literature from behavioral economics also. So to answer your question, I would say still we want to take more perspective from this human modeling perspective. And it would be ideal to even do this text with a human to see what's really going on in this stochastic decision or sequential decision-making setting. That was a goal, actually. And that's also the point we want to distinguish us from many of the multi-agent RL literature at the point.
One more question?
Just so for my understanding, what you're maximizing with respect to your opponents is your own Q value with respect to your belief about how your opponent is behaving, what their strategy is.
Right.
Now, if I want to be cooperative, then the idea here is that I'm getting a reward for me, for myself, and for my opponent, and that's how I'm cooperating here. Do you think there's something we can do better if we know that our opponent is using the same learning algorithm, there's the symmetry this way, that we could cooperate better with them given that we know that they're also learning the same way?
Yeah, I think that's possible. That's a very good point. One thing I have to mention here is that all the results we are talking about here are only convergence to Nash equilibrium, or like a Nash equilibrium in the sense that just one equilibrium. First of all, we don't know how good that is. Second of all, it's not, even in a cooperative setting I'm talking about, it's not convergent to like a team optimal solution, for example. That's very hard. In other words, like the equilibrium selection problem there, or like, how to make sure your learning dynamics is, of course, natural and also convergent to a better equilibrium, that's in general a very hard problem. So there are some literature in the static learning games literature. If you follow certain like neural learning dynamics in like a certain type of games, you can convert to the equilibrium with a better social welfare. But in here, in stochastic game, we are not sure yet. But that side information you mentioned, I think should probably be very useful. Because you are allowed to, one key challenge in coordinative setting is that you don't know what the opponents are really choosing. But if you know that, you may possible to see like the big table, payoff table, you should be able to locate a larger like equilibrium point than the fully decentralized case. So I would say that's very promising. Thank you. Thank you all very much.